Hi everyone, welcome to NEET Selection Express at Physics Wallah. This is Sagar Darvi, your chemistry teacher, and I welcome you to this course of organic chemistry. Well everyone, I'm sure that you all are aware that in this NEET Selection Express, we have been discussing all previous year questions, along with which we are also discussing some most important questions for that particular chapter. So in every session, we are trying to cover all the important PYQs along with some more important questions. So likewise, today as well, in our another important chapter of organic chemistry, which is aldehydes, ketones and carboxylic acid, we will be discussing about previous year questions along with some important questions. So let's proceed with our today's first question right on your screen from NEET 2020. So guys, the question says, identify compound X in the following sequence. Well, if you observe, they have given toluene, and on arrow the condition which they have mentioned is Cl2H nu, which is producing compound X, which upon further hydrolysis producing benzaldehyde. Well guys, toluene along with Cl2H nu indicates that chlorine in presence of UV light will produce free radical. So this is a free radical condition. And in toluene, when you carry out chlorination via free radical mechanism, chlorination takes place at the position where free radical is most stable. So in a toluene, the stable free radical formation will take place at benzylic carbon. So suppose if I'm talking about intermediate here, X, the intermediate could be a benzene. And at this carbon, we have to carry out chlorination. Now, at benzylic carbon, we are having 3 hydrogen atoms, meaning ideally speaking, if you carry out free radical chlorination, all the 3 H's can be replaced. But do we really have to substitute all the 3 H's with the chlorine or not? That depends upon our product. Well, guys, if you observe this product here, this product indicate benzaldehyde, which means at benzylic carbon, we are having 1 hydrogen intact, and then there is double bond O here. That indicates one of the hydrogen atom in the toluene is still intact. So let's write that. And the 2 H's have been substituted by 2 chlorine. And now if you carry out further hydrolysis, this indicates that these 2 chlorines are then, upon hydrolysis, get substituted by 2 OHs, so we'll be getting C, H, and the 2 valency which are now seems to be substituted by chlorine will be satisfied by OH, and that's how we get formation of diol. We know the fact that diol is always unstable, hence such unstable diol then immediately eliminates water molecule, so that bond between O and H will shift back between the carbon and oxygen, and that is how we will get formation of benzaldehyde. So guys, how many hydrogens of toluene we have to substitute by free radical chlorination, that will always dependent upon what product are they expecting from us. If the product expected is aldehyde, then we have to keep 1 hydrogen intact and substitute remaining 2 hydrogen with chlorine. Imagine had it been the case where the product asked, suppose would have been benzoic acid, meaning we would have replaced all the 3 H's with 3 chlorine, we would have got CCl3, which upon hydrolysis would have produced triol, out of which 2 OH's upon elimination of water would have produced C double bond O, and even this H would have been OH, so in that case we would have got benzoic acid. So toluene upon chlorination produces a product disubstituted, which upon hydrolysis will give you diol, and eventually will get benzaldehyde. So X, which they are asking us in the question, is nothing but CHCl2. That is question number 1 from the chapter aldehydes, ketones and carboxylic acid. So everyone, without wasting much of a time, let's get started here with the question number 2. You can see NEET 2013 question, that is question says reaction by which benzaldehyde cannot be prepared. Okay. If you see the first reaction given, benzene plus carbon monoxide plus HCl in presence of anhydrous AlCl3, this is Gattermann-Koch formylation. So HCl plus AlCl3 will produce H plus. H plus upon attack on CO will form C double bond OH, that is formyl group, which introduced at benzene, and that's how you get formation of benzaldehyde. So this will certainly form benzaldehyde. So this cannot be our answer, because everyone, we want a reaction which is not forming benzaldehyde. Second, they've given us some benzoic acid upon reaction with zinc amalgam and concentrated HCl. Well, when we talk about zinc amalgam and concentrated HCl, this reminds us of a reaction called Clemenson's reduction. And Clemenson's reduction is a reaction where carbonyl carbon is reduced to methylene group, that is CH2. Meaning if I have been given benzaldehyde and if I carry out Clemenson's reduction, we'll be getting toluene. If we have been given acetone, acetophenone, so that C double bond O will be reduced to further CH2 to give you ethyl benzene. Which means this reaction nowhere is resulting in the formation of benzaldehyde. So this is going to be our right choice. But let us verify B, C and D as well. See here, CH3 plus CrO2 Cl2 in CH2 followed by hydrolysis. This is Ettard reaction, right everyone? So this reaction that they're talking about is Ettard reaction. And Ettard reaction is a method of formation of benzaldehyde, meaning this will produce benzaldehyde. So not our right answer. Benzoyl chloride upon passing hydrogen gas in presence of palladium metal coated over barium sulfate is what you call it as Lindlar's catalyst. So yes, benzoyl chloride upon passing hydrogen gas in presence of Lindlar's catalyst will produce benzaldehyde. So even this will produce benzaldehyde. The only reaction that won't result in the formation of benzaldehyde is option B. Hence, choice B is the most appropriate choice for us for this question. Okay. Proceeding further with next question, number 3. Which one of the following can be oxidized to the corresponding carbonyl compound? Okay, guys. Let us start with the first option given here. 2-hydroxypropane. Well, 2-hydroxypropane is nothing but propane-2-ol. Yes, this is propane-2-ol. You can say alcoholic OH is connected to secondary carbon atom. So this is 2-propanol. Imagine if this 2-propanol is treated with oxidizing agents such as PCC, PDC, Collins reagent, or copper at 573, or probably even if you take Jones reagent, that is a strong reagent. But since alcohol is secondary, if you oxidize it with all the mild oxidizing agent and several strong oxidizing agent, then secondary alcohol upon oxidation gives you ketone. So simply, just for the sake of understanding, imagine from OH if you remove this H, and from the secondary carbon if you remove H, between carbon and oxygen we'll get formation of double bond. So we will get formation of CH3CCH3 double bond O. So we got formation of acetone. That's what they're asking, which one can be oxidized to the corresponding carbonyl compound. So yes, option A is certainly forming carbonyl compound. Let's check with B, C and D. Orthonitrophenol. Well, orthonitrophenol won't be oxidized to ketone, nor phenol will be oxidized to ketone. And option D that they have given us is a tertiary alcohol. Everyone see here, tertiary alcohol, 2-methyl-2-hydroxypropane. So let's say this is propane carrying hydroxy at number 2 and methyl at number 2. 2-hydroxy 2-methyl propane. So if you observe in tertiary alcohol, at the carbon carrying OH, there is no hydrogen atom present here. Since there is no oxidizable H present, tertiary alcohol does not undergo oxidation, whether we use mild oxidizing agent or strong oxidizing agent. Only copper, if we heat tertiary alcohol with copper at copper at 573 Kelvin, that is at 300 degrees Celsius, then this undergoes dehydration to produce alkene. Do remember that. Otherwise, tertiary alcohol is not going to show reaction with any of the oxidizing agent. Hence, the only option given which can be oxidized to carbonyl compound is the secondary alcohol, isopropyl alcohol, or can be called as 2-hydroxypropane. Next question, number 4 for you all on your screen. Alright guys, this looks interesting. NEET 2017 question it is. Okay, some unknown compound is given, C2H6O, which means this compound looks like of the general formula CnH2n plus 2. dot O. Guys, not to forget, this is the general formula that correspond to alcohol or ether, which are isomeric with each other. Well, so your starting compound has to be either of these two functional group. That compound upon reaction with copper at 573. Well, so we got our hint that if they're talking about copper at 573, which means they're talking about oxidizing agent. So among these compounds which get oxidized with the copper are alcohol, which means certainly this compound is going to be alcohol because oxidizing agent is mentioned. So let us assume alcohol containing 2 carbon atom is ethyl alcohol, which upon oxidation is giving you A. So ethyl alcohol upon oxidation with mild oxidizing agent, it will produce acetaldehyde. And well, this guess of ours is fitting well because after an aldehyde is obtained, you can see the next reagent that they have given is a Tollens reagent. So we can now write it down. Like we said, we figured out that this functional group, this molecular formula correspond to this general formula, which correspond to either alcohol or ether, which means this could be either of these two. Looking at this copper at 573, which is mild oxidizing agent, this has to be alcohol. So CH3, CH2OH. Upon mild oxidation, you'll get A. Number of carbon remains same, but primary alcohol get oxidized to aldehyde. Here A is acetaldehyde, or you can call it as ethanol. Now you can see ethanol contain hydrogen atom connected to carbonyl carbon. Such hydrogen which is present at carbonyl carbon atom, we call it as oxidizable H. Hence, this can be oxidized by some other oxidizing agent like Tollens reagent, Pelling solution, Benedict solution, or Schiff's reagent. And they are saying that silver mirror is observed, which means this has to be A, meaning this has to be aldehyde. So that aldehyde containing 2 carbon is further treated with OH minus. So this has to be OH minus. And heat. So this is an aldehyde which contains alpha hydrogen atom, which upon treated with OH minus, it shows its characteristics reaction that is called as aldol condensation. So imagine if you have been given two molecules of acetaldehyde, and if you subject it to aldol condensation, what is going to be product? Everyone, I'm sure when you learn this chapter, aldehydes and ketones, and when you studied aldol condensation, you must have learned a trick of writing the product directly. So imagine if I take 2 molecules of acetaldehyde, CH3CH double bond O, assuming that this is carbon and acceptor, and on the other hand CH3C double bond OH, and we expose carbonyl oxygen with aldehyde of other carbon, and at the alpha carbon we are highlighting 2 of the H's. And imagine if we carry out condensation, so the product obtained would be CH3 CH double bond CH and C double bond OH. So if you assign IUPAC name to this compound commonly also known as crotonaldehyde, but according to IUPAC 1, 2, 3, 4, but2-enal, but2-enal. So why is but2-enal? And the same compound aldehyde upon reaction with semicarbazide will produce semicarbazone. So imagine if this is acetaldehyde and we are treating that with semicarbazide. So we can write it this way: H2N NHC double bond O NH2. And if we condense it like this, the product is going to be CH3 CH double bond N NHCO NH2. That is nothing but semicarbazone. So yes, now the question that they are asking, identify A, X, Y, and Z. So you have to first identify A. The starting compound is not A. A is this one. What is it? Acetaldehyde, meaning ethanol. So the first compound has to be ethanol. So straight away among all the options given, only B is saying so. A is ethanol. What is X? Ethyl alcohol. What is Y? Well, Y is but2-enal, which we saw there. and Z is semi-carbazone, the one which we got here by the reaction between these two. So wonderful question. This was asked in 2017, and the option which matches with this is option B. All right, everyone. Okay, guys, we are moving forward with the next question, number 5. Of the following, which is the product formed when cyclohexanone undergoes allyl condensation followed by heating? All right, guys. This is double bond. So basically, question is we have to identify which of the following product is the allyl condensation product of cyclohexanone. So like we applied the trick in the previous question, where 2 molecules of acetaldehyde we subjected to allyl condensation to get the product. And how did we get the product? We exposed the carbonyl oxygen of one aldehyde with 2 alpha hydrogen atom of the other aldehyde, which is called as carbanion donor, and the first one was called as carbanion acceptor. So let's do that here as well. So let's assume we are having first molecule of cyclohexanone exposing this carbonyl oxygen to the alpha hydrogen atom of second molecule of cyclohexanone. So you can see the first one's carbonyl oxygen will be condensed with the 2 alpha hydrogen of second cyclohexanone. And that's how we can directly get the product by remole of water. If we do that, of course, in an alkaline condition upon heating, we will be getting the double bond and double bond O. So that's the product. Which option fits well with that? Well, straight away option A. So guys, see, that's how, if you know that how are we going to get the final product directly from allyl condensation, it will save a lot of our time. That's why whenever any question asks us to write down the product of allyl condensation, expose the carbonyl oxygen of one aldehyde with alpha Hs of other aldehyde, remove water, that is going to be your final product. All right. So next question, number 6. The product formed by the reaction of aldehyde with the primary amine. Okay. So this is the reaction, we call it as reaction of carbonyl compounds with the ammonia derivatives. So again, if we have to write down the reaction, we can put it this way. Reaction of an aldehyde, RC double bond OH with primary amine. Primary amine is written as H2N R dash, which is generally treated in a weakly acidic medium. So to write the product, we simply write it as carbonyl oxygen is condensed with the 2 hydrogen atom of primary amine, and that's how this will result in the formation of RCH double bond bonded to NR dash, and this is what we call it as Schiff's base. So observe the options and see which fits well here. Product of reaction of aldehyde with the primary amine will result in the formation of Schiff's base. Well guys, remember, Schiff's base and Schiff's reaction are two different things. Schiff's reaction is basically decolorized solution of P rose aniline hydrochloride salt solution, which is the pink magenta color, which upon reaction with sulfur dioxide decolorizes and you get the colorless solution. That is what we call it as Schiff's reaction. Okay, this is Schiff's base, two different compounds altogether. Next question, number 7. Which one is the most reactive towards nucleophilic addition reactions? 2014 question this is. Okay, everyone, let us see the general mechanism, a concept to understand this question. So let's say if we have some carbonyl compound And if we allow this to react with strong nucleophile, let's say anionic nucleophile we have got. So across carbon and oxygen, O being more electronegative acquire delta minus and carbon acquire delta plus charge. Such carbonyl compounds, when brought in contact with strong anionic nucleophile like Cn minus, then that nucleophile attacks at the deficient carbon and this pi bond breaks. This step where attack of nucleophile takes place at the carbon is experimentally found to be slow step and rate determining step. So as a result of attack, what do we get? Well, we have got carbon with 2 bonds, and now here there will be nucleophilic attack, and we'll be getting single bond O minus. This single bond O minus then accept a protic part from either nucleophilic parts, protic part, or from solvent, and that's how we get formation of a product like this. Well, the whole idea here is, in a rate determining step, nucleophile is attacking at the carbonyl carbon atom. So imagine if this carbonyl carbon is more deficient. So the rate of attack of nucleophile at the carbonyl carbon depends upon 2 factors. One is called as steric factor, other is called as polar factor. Steric factor meaning, if we have smaller group present at this carbonyl carbon atom, when nucleophile will attack here, the unsaturated carbon is going to become a saturated carbon. Meaning the bond angle which was 120 for the sp2 hybridized carbon is going to become 109.5 because this is saturated carbon. So if the 2 groups present here are bulkier, then those 2 bulkier groups here are separated by angle of 120 and here they will be separated by 109.5, meaning bulkier group will come relatively closer. As a result of which the product form is not going to be that stable, meaning the group attached at this carbonyl carbon has to be smaller in size so that steric hindrance will be lesser. That is one of the factors. Second factor is polar factor, meaning electronic factor. More deficient the carbonyl carbon is, faster the attack of nucleophile and the reaction proceeds in the forward direction. Equilibrium will be driven in the forward direction. So for nucleophile to be able to attack at a faster rate here, this carbon should be more deficient. Now all the examples that they have given, out of which 3 are benzaldehyde. One, this is benzaldehyde. This is also benzaldehyde. Only this is ketone. So comparing aldehydes with the ketone, imagine if you just have R and H here. So with respect to polar factor, it is only one alkyl which will donate electron via plus I and decrease the deficiency of carbon. So rate of attack of nucleophile will be decreased. But in ketone, even this H is going to get substituted by R. Both will show plus I and the deficiency will be decreased to the maximum extent. So attack of nucleophile will be at a slower rate. So ketone will always give you reaction at the slower rate. Now among these 3, because everywhere there is a carbon of aldehyde, but on the ring there are some substituent present here, out of which nitro group, we know the fact it is a very strong electron withdrawing group. If it's a strong electron withdrawing group, it will withdraw electron from this carbonyl carbon atom, which will make this carbon more deficient. So the delta plus charge at this carbon will increase due to EWG. Greater the delta plus charge at the carbon, faster the attack of nucleophile. Hence, D is going to be most reactive among all the options towards nucleophilic addition reaction, which is the characteristics reaction of aldehydes and ketones. So guys, right choice is option D. Moving forward with question number 8. Predict the product in the given reaction. Alright guys, I want you all to first focus at the question and think of what reaction is this. Because in this chapter of aldehydes and ketones, carbonyl compound and OH minus, there are several reactions which we have seen like that. So how do we identify that which reaction it is? So we know the fact that in presence of OH minus, there are 3 prominent reactions. Other part of reaction might change. One is haloform reaction, where again we are having OH minus. Second, we have got aldol condensation, and then there is Cannizzaro. All reactions we have seen that takes place in presence of OH minus. How do we identify which reaction it is? Well, you have to look for the substrate. Substrate given is benzaldehyde carrying chlorine at meta position. So benzaldehyde is such a substrate which does not contain alpha hydrogen atom. When aldehyde containing no alpha hydrogen atom is treated with 50% KOH, we know that they undergo Cannizaro's reaction. Cannizzaro reaction is a disproportionation reaction, which means two molecules of metachlorobenzaldehyde will undergo redox reaction. One will be oxidized, other will be reduced without any change in the number of carbon atom. So let's say if one of the molecule is oxidized, then upon oxidation this aldehyde group will be converted to COO minus and chlorine will be at meta position. We get carboxylic acid, but then in presence of alkaline condition we get its conjugate base and the other will be reduced without any change in the number of carbon, meaning carbon will remain same, chlorine at meta position, and this aldehyde group will be reduced to primary alcohol, that is CH2H. So just observe which option is saying this as option. Yes, look at option C. There is benzyl alcohol carrying chlorine and there is benzoate ion carrying chlorine at meta position. Option C is the most appropriate choice. Guys, I'm hoping that you are understanding what we are discussing here. This question was from Cannizaro's reaction. Next question, number 9. Acetone is treated with excess of ethanol in presence of hydrochloric acid. The product obtained is, well, this is again addition reactions of aldehydes and ketones. So aldehydes, ketones, upon addition reaction with alcohols in presence of dry HCl first forms hemiacetal. Upon reaction with second molecule of alcohol, it then gets converted to acetal. So if I have to write reaction with excess of ethanol, I have to consider that there are two molecules of ethanol reacting. So we can write reaction like this. Let's say we are having acetone. And we are treating with two molecules of ethanol. First and second. This reaction takes place in presence of dry HCl. So in presence of dry HCl, well, we are skipping the mechanism and directly writing the product. What we have learned is we expose carbonyl oxygen to 2 protic H of alcohol and we remove water from here. So upon elimination of water, we will be getting formation of CH3CCH3. One of the valencies is satisfied by ethoxy group OC2H5. And other is also satisfied by OC2H5. So this is what we call it as acetal, or rather ketal formation, because starting upon is ketone. So it's a ketal of acetone. So which option says so? You can see that here. Two molecules of alcohol, because they said excess, treated with ketone in presence of dry HCl to give you ketal formation. Answer option is D. Moving forward with the next question, everyone. Okay. The question is acetaldehyde CH3CHO and C6H5CH2CHO can be distinguished chemically by. Okay. Well, one thing you have to understand, both the compounds containing functional loop, aldehyde. So both contains identical functional loop. So the reaction which is shown by the functional loop aldehyde will not be able to distinguish these two compounds because both of them are containing aldehydes. For example, well, guys, hold on. We'll do small correction here. Let's say here, I'm making this reagent as toluenes. Okay, so now if you see, like we said, both contain aldehyde functional group, so the reaction which are characteristics reaction of aldehydes won't be able to distinguish these two compounds because both of them are containing aldehyde functional group. So Fehling test, Tollens reaction test, and the Benedict test are the three tests which are the characteristic test of aldehyde. Meaning, if we allow both of this compound to react with this three reaction, we are going to get formation of product which is going to be their corresponding acid and the corresponding color. Like if you use Tollens reaction, we'll get silver mirror formation. Both of them will form silver mirror. If you take Benedict or Fehling, both of these can form red precipitate of CO2. So we won't be able to distinguish using this three reaction. But iodoform test is the test which is shown by compounds containing methyl keto group. So methyl, when connected to C double bond, only those compounds are capable of showing a haloform test. So among these two options, you can say first is acetaldehyde. So acetaldehyde will show positive haloform test, but here 2-phenyl ethanol won't be able to show that reaction because there is no methyl group present, methyl keto group present here. Hence, I will say iodoform test can distinguish these two substrates. So the right choice is option C. Next question, guys, straight away here. Reduction of aldehydes and ketones into hydrocarbons. Well, they're talking about reaction of aldehydes and ketones, meaning they're talking about conversion of carbonyl compounds into hydrocarbons, meaning converting carbonyl compound into methylene group using zinc amalgam and concentrated HCl. Zinc amalgam in concentrated HCl is the reaction, we call it as Clemenson's reduction. So the right choice is option D. Straight away, it is an informative reaction. Brestol reaction, just for information. Well, when we talk about cope reduction is a cope elimination, it should have been. It's elimination reactions of amine oxide. Likewise, Dow's process is the process of chlorobenzene upon with aqueous NaOH under drastic condition. And Wolff-Kishner is again the same conversion, carbonyl carbon to CH2, but it is an alkaline reagent where we treat carbonyl compound with hydrazine first, followed by treatment of KOH in presence of glycol. But zinc amalgam and HCl is a Clemenson's reducing agent, hence the option is D. Okay, everyone go through the question once again here. Okay, question says, which one of the following on treatment with 50% aqueous NaOH yield corresponding alcohol and acid? All right, guys, what do we understand from this question? 50% aqueous KOH with sodium hydroxide giving you alcohol and acid, which means, aren't they talking about Cannizaro's reaction? Cannizaro's reaction. And Cannizaro's reaction is a characteristic reaction of those aldehyde containing no alpha H's. Containing no alpha H's. So we'll have to just identify which aldehyde doesn't contain alpha H. Starting with option D, aldehyde, there is alpha carbon carrying 2 H's. Ketone, it has got 2 alpha carbon, each carrying 3 H's. Propanaldehyde, again carrying alpha carbon carrying 2 H's. It is just a benzaldehyde where there is alpha carbon but there is no H present. Imagine if we represent it. So we will write it like this. Yes, you see, there is alpha carbon here, but there is no hydrogen present. Hence, such compound is eligible to show Cannizaro's reaction. Hence, everyone, option A is the right choice. That was question number 12 asked in 2007. Guys, moving forward with the next question from carbonyl chemistry. A product formed in aldol condensation is which of the following? Okay. If you look at the option, they're talking about some hydroxy group in aldehyde either at alpha or beta position. So what do you think is going to be product? Let's do one thing. Carry out allyl condensation. All right. Imagine if you're having acetaldehyde. We are highlighting one of the alphides. Treating this with base. So fast abstraction of alpha hydrogen will produce carbon ion. We have got H, C double bond O, CH2 electron pair minus. This carbon ion is then allowed to attack at carbon ion acceptor, that is second molecule of acetaldehyde, let's say. So carbon ion attack at carbon bond breaks towards O, making it O minus. So this will form, starting with this H, C double bond O, CH2 bonded to CH single bond O minus, which is further connected to CH3. This O minus then accept H plus from solvent and becomes alcoholic OH. So we'll be getting aldehyde, CH2, CHOH and CH3. Now this is the intermediate compound which we have got, and they're asking question with respect to this intermediate compound only. So our priority functional group is aldehyde, adjacent carbon is alpha, and this is beta. So at beta carbon we are having hydroxy group. So the compound will be called as beta hydroxyaldehyde. Beta hydroxyaldehyde. Now let's check the option. The product form in allyl condensation. Before we condense it, we have got this intermediate. So beta hydroxyaldehydes or beta hydroxyketone. Absolutely, this is our answer. It is not alpha. Hydroxy is not at alpha. Hydroxy is at beta position. Again alpha, so this cannot be correct. Beta hydroxy acid, well, acid is not our product. The right choice here is answer option A. Next question, dear students. A carbonyl compound reacts with hydrogen cyanide to form a cyanohydrine, which on hydrolysis forms racemic mixture of alpha hydroxy acid. The carbonyl compound is. Okay, hold on. First of all, we need to recognize what reaction is that. Let's take a general substrate here. Let's say we are having C double bond O. We don't know what valences these are, but we are treating this with HCN. This reaction we generally carry out in presence of alkaline medium. Okay. For the understanding purpose, we are not writing detailed mechanism, but let's assume cyanide being nucleophile attacked at deficient carbon, this bond breaks over O, making it O minus, which accept H plus. So if I write down product directly, we get C at this carbon cyanide attacked, and here we've got OH. Okay. Now they are saying this is further hydrolyzed to form racemic mixture. When they say this is further hydrolyzed, let's say I'm carrying out acid hydrolysis and we're getting racemic mixture, meaning the product obtained has to be optically active. First of all, cyanides upon hydrolysis produce carboxylic acid, COOH, and this is OH. Now if I'm saying that this compound is obtained as a racemic mixture, which means this compound form must be chiral. So this carbon over here has to be a chiral carbon atom. And for this carbon to be a chiral carbon atom, these two valencies which we haven't satisfied has to be two different valencies. So our starting compound should be a compound having two different valencies. So let's see which option is saying that the two valencies are different. The first example which they have given us is formaldehyde. In formaldehyde, both the valencies are identical, which means the product is not going to be chiral, so this is not our choice. Second is acetaldehyde. Yes. In acetaldehyde, these two valencies are different, meaning this is our right choice. So answer is certainly going to be B. Let us verify the option C and D as well. See, acetone. Acetone is dimethyl ketone. So not our choice because both are identical valencies. Third is diethyl ketone. Both identical valencies, so not our choice. Hence, everyone, optically active, that is racemic mixture, will be obtained from option B here. So that is our right choice. Question number 15 here. A and B in the following reactions are. A and B in the following reactions are. Okay. Well, observe here. This question is exact. This reaction, first one, is what we saw just now. Addition of HCN. Let's do that here again. So H plus Cn minus, let's say Cn minus attacked at carbonyl carbon. This bond have been broken towards a O, making it O minus, which will accept H plus from here. So A is going to be, this A will be R, hold on, R, Cr, the cyanide attacked here. This became single bond O, which accepted H. Okay. And this compound A is further treated with B. And if you observe the product, let's call this is R and R dash. So this is R and R dash. So R I can see here, R dash I can see here, OH I can see here. Meaning the change that has taken is with respect to Cn. Cn have been converted to CH2NH2. If you observe this change, Cn is converted to CH2NH2, which means they're talking about we are carrying out reduction. So somehow a reduction of nitrile have been carried out to give you primary amine. Meaning the reagent B that we are using here has to be a reducing agent. A is what we have got here. So let's observe A and B respectively if they want. Where do they say that A is what we have got? Well, so this is ruled out because in A there is no carboxylic acid. Well, this could be A, R dash. Even this cannot be A because we need one of the group as OH. This could be A. So option A and C are ruled out. Between B and D, B is a reducing agent. Here they are saying B is hydrolyzing agent, not a choice. But yes, here we have got reducing agent lithium aluminium hydride. Hence, the most appropriate choice, which is talking correctly about both A and B, is option D. Next one, guys, for you all, number 16 from 2002, year 2002. The given two structures are related to each other as what? Okay. Here there's CH2 carrying electron pair, meaning the formal charge has to be -1 charge. So when I observe these two structures, I can see negative charge of carbon is in conjugation with the pi bond. Negative charge alternate pi bond. So in such case, electron density flows from highly dense area to low density area relatively. So negative charge will delocalize. Pi bond will break towards O, forming carbon-carbon double bond. Double bond will become single bond. And oxygen, which was otherwise carrying 2 lone pair, now will carry total 3 lone pair. As a result of which, this will become anionic oxygen. So yes, these two structures are resonating structures of each other. The right choice is option A. These two are resonating structures. If we would have removed hydrogen from here and added hydrogen here, in that case, atom would have migrated from one of the carbon to other carbon. So in that case, we wouldn't call it resonance. We would call it tautomer. But here there is no change in the position of atom. Only electron density has been dispersed from one part of molecule to another part of molecule. Iodoform test is not given by. Well, if you observe the options given, either it is aldehyde or alcohol or ketone. So let me remind you, when you talk about compounds showing haloform reaction, well, I'll list it down for you guys so that it is helpful for you next time when you revise a haloform reaction. When you talk about aldehyde, remember only aldehyde that shows haloform reaction is acetaldehyde. Meaning ethanol. No other aldehyde shows haloform reaction. About ketone, all those ketones whose IUPAC name will be written in the form of alkane to one will show haloform reaction. If you talk about alcohols, only primary alcohol that shows positive haloform reaction is ethyl alcohol, and secondary alcohol that shows positive haloform reaction should be in the form of alkane to ol. Fine. Now let's observe the option and see which option fits into these names. So first one is ethanol. Ethanol is the IUPAC name of acetaldehyde, meaning this is going to show haloform test. Hence not our correct choice because we want the one which does not give haloform. Next is alcohol. Among primary alcohol, only alcohol that shows haloform is ethyl alcohol, meaning ethanol. So this will show haloform test, not our choice, because we want something or the compound which does not give haloform. Next is pentane 2-one. See, pentane 2-one meaning this molecule is fitting into this IUPAC system, alkane 2-one. Pentane 2-one meaning even this will show haloform test, not our right choice. But D is not fitting into the way ketone should exist. Pentane 3-one meaning it is like this. So in pentane 3-one we don't have methyl group adjacent to keto. For compound to show haloform reaction, we need to have methyl group adjacent to ketone, and that's how it becomes alkane 2-one. So where it is pentane 3-one meaning this will not show haloform test, hence it is the right choice for us. That's what they are asking, which compound will not show haloform. Pentane 3-one because it does not contain methyl keto group. Next, question number 18. The oxidation of toluene in presence of CrO3 in presence of acetic anhydride gives a product. So toluene upon CrO3 in presence of acetic anhydride gives a product. Well guys, this reaction is formation of aromatic aldehyde. So the product is going to be benzaldehyde. There are three reactions which helps us to form aromatic aldehyde. One is retard reaction, where we take toluene, treat that with CrO2Cl2 in CS2. We get benzaldehyde. Second, this reaction, we take toluene, treat that with CrO3 in presence of acetic anhydride. And third reaction is the first question that we solved in today's class, that is toluene upon controlled chlorination. So at benzylic carbon, 2 hydrogen will be replaced by chlorine followed by hydrolysis. So yes, we have identified that toluene with CrO3 will give you benzaldehyde, and that compound is further treated with aqueous NaOH. Well, so the question that they're asking about here is benzaldehyde which is treated with aqueous NaOH. So let's assume two equivalent of benzaldehyde react with aqueous NaOH. One of the benzaldehyde will be oxidized to give you conjugate base of benzoic acid, that is benzoate, and second molecule will be reduced to produce benzyl alcohol. So that's how benzaldehyde undergoes disproportionation to form oxidized form, that is benzoate, and the reduced form, that is benzyl alcohol. So among the option, if you observe, this option is talking about benzoate ion, hence a right choice. So basically the question that they have asked were mixture of two reactions. First was formation of aromatic aldehyde and second one was Cannizaro's reaction. So this reaction is Cannizaro's reaction. So everyone, next question, number 19 for you all. Okay, the reaction that does not give benzoic acid as the major product. So we don't want benzoic acid as the product. We do not want, does not give benzoic acid. Okay. Well, the first reaction that they say, looking at the reagent, benzyl alcohol upon reaction with K2Cr2O7. This reaction is, or this reaction rather, is a reaction of alkyl benzene with strong oxidizing agents such as acidified dichromate, acidified KMnO4, or even concentrated nitric acid. So this reaction says if you use such a strong oxidizing agents and if your substrate contains alkyl benzene carrying benzylic carbon with at least one hydrogen atom, then it straight away undergoes oxidation to produce benzoic acid irrespective of the length of chain of carbon atom. So how many carbons are present in this side chain does not make any difference. If we have benzylic carbon carrying at least one H, it will be oxidized to benzoic acid, meaning this will produce benzoic acid, so not our choice. Right? Next one, if you observe here, they have given us acetophenone and NaOCl, meaning they are talking about haloform reaction. So how do we write product of haloform reaction? Well, simple trick I'm sure everyone must have studied. Well, I'll correct this COCH3. I'll try to write it in a little different way so that understanding reaction would be easier for us. So suppose if I write it like this, C double bond O CH3. And if I'm carrying out haloform reaction with this, then in haloform reaction, what do? We break the bond between methyl and keto. And then the methyl part forms its corresponding haloform and the remaining part forms conjugate base of carboxylic acid. Meaning product of this reaction will be conjugate base of carboxylic acid plus haloform reaction, that is CHCl3. Once this is obtained, second condition hydrolysis, so this will be protonated. I'm directly writing here. So we'll be getting COH. Meaning haloform reaction will help us to form benzoic acid if our substrate is acetophenone. So this cannot be our choice because they are saying we do not want benzoic acid as the product. Option D, well, just now when I explained this reaction, I said if we take any compound having benzylic carbon with at least H and strong oxidizing agent like acidified dichromate or acidified KMnO4 or concentrated nitric acid, this will be oxidized to straight away benzoic acid, meaning here also we are going to get formation of benzoic acid. So here as well as here, we will be getting benzoic acid, hence this is not our choice. Option C, benzyl alcohol with PCC. Well, now looking at all the other options have been ruled out, meaning this has to be answered. But let's justify why. PCC, everyone, is a mild oxidizing agent. It's a mild oxidant. So mild oxidizing agent will oxidize primary alcohol into aldehyde. This is going to be C double bond OH. The right choice is option C. Moving forward, next question. 2007 question, that is, consider following compounds, and they're asking what is the correct decreasing order of the reactivity towards hydrolysis. Well, guys, acid chloride have been given and they're talking about hydrolysis reaction, meaning again they are talking about reaction of carbonyl carbon. So few minutes back when we discussed this question, we saw the reaction was where cyanide attack will take place at a faster rate. So even hydrolysis, meaning we'll be using water as a nucleophile here. So whichever carbonyl carbon is more deficient, hydrolysis will take place at the faster rate over there. So if you look at all the options given, this is carbonyl carbon everywhere. So we'll see the magnitude of positive charge at the carbonyl carbon. The magnitude of positive charge here at this carbon will be defined by the group which is present here. So nitro is the strongest electron withdrawing group because it shows -m. Then there is aldehyde, which is second best electron withdrawing group, which will also withdraw electron via -m. But the intensity of nitro is better than aldehyde. After this, in this benzoyl chloride, we don't have any group. But here we are having methyl group, which will show +H. +H meaning it will donate electron and the delta plus charge will be decreased. So 3 is going to be the least reactive. 3 is least reactive. Because deficiency at this carbonyl carbon will be neutralized. So it is not that deficient, so nucleophilic attack won't be preferred. Because nitro is most withdrawing, 2 is most reactive. After 2, it is going to be 4th, the next one. And after 4, it is going to be 1. Because in 1, at least there is no electron donating group present, so it's going to be 1. The right choice is 2413. 2413. You can see that here 2413 is the right choice. Option C. Alright. Well guys, next question number 21. In the above reaction, the product P is, I guess this is a pretty straightforward, the most simplest question among all. This reaction can be considered as a reaction from aryl halide as well, where we convert aryl halide into Grignard reagent and then further treat with dry ice or solid CO2. So see, that's what is happening here. We have phenyl magnesium bromide. In phenyl magnesium bromide, bond between carbon and magnesium is considered to be having more ionic character. So metal will always release its electron to carbon of benzene ring. So this will be anionic and this will be Mg plus Br minus. And this is then treated with CO2. C double bond O, double bond O. In this CO2, because O is more electronegative than carbon, it will acquire delta minus, carbon will acquire delta plus charge. The anionic carbon will then attack at the carbon. This bond will break towards O. So we will be getting formation of phenyl ring connected to C double bond O. Single bond O minus, which will be then acidified to give you COOH. So yes, our product is going to be benzoic acid. And here is that option B, which is talking about benzoic acid. Next one, number 22 for you all. Guys, just go through that. It's NEET 2018 question for you. Okay. Via little correction, guys, via intermolecular. Hydrogen bond. Okay, guys, look at the question now. Carboxylic acid have a higher boiling points than the aldehyde and ketones and even that of alcohols of comparable molecular masses. It is due to their ability of what? I mean, we have seen that the boiling point property is directly related to the intermolecular association among the molecules. So if I talk about carboxylic acids, so we know that in gaseous state carboxylic acid exists as a dimer, which we represent like this. This is first molecule of carboxylic acid and I'm representing second molecule of carboxylic acid here. So see here, first molecule of carboxylic acid has oxygen hydrogen bond where due to differences in the electronegativity, hydrogen will carry delta plus charge. In the second molecule across oxygen hydrogen bond, oxygen carries delta minus and hydrogen carries delta plus charge. So such deficient hydrogen atom, when comes in the vicinity of oxygen carrying at least one lone pair, this form intermolecular hydrogen bond. So due to intermolecular hydrogen bonding, this molecule of carboxylic acid is existing as a dimer. As a result of dimer formation, its boiling point is going to be very high. So the question now is, carboxylic acids have higher boiling points than aldehydes ketone, and also in comparison to alcohol having comparable molar mass, is due to ability of carboxylic acid to form intermolecular hydrogen bonds. Yes, option D is the most appropriate choice here. For question number 22. Next one, number 23 here. The correct order of strength of carboxylic acid is, well guys, this question is more of general organic chemistry. So if you just revisit the concept of finding out the order of acidic strength, we have always been saying compound is acidic when its conjugate base is stable. So to check the acidic strength, we convert all those acids into their conjugate bases and we check the stability of conjugate bases. Whichever conjugate base is more stable, that corresponding acid is considered to be a relatively stronger acid. So what we are going to do, we will assume that from all the acid H plus is lost and we'll check the stability of this conjugate base. Same we will do it here. H plus is lost, CO minus. H plus is lost, CO minus. And now the stability of anion depends upon the dispersal of a negative charge. Dispersal of negative charge meaning how well this charge can be withdrawn by the group present in the side chain of carboxylic acid decides how well this anion is going to get stabilized. So if you look at option 2 and 3, to this CO minus there is cyclic ring present carrying oxygen. Guys, not to forget, oxygen is an electronegative atom that can withdraw electron. Withdrawal of electron meaning this negative charge will be dispersed by the oxygen. Dispersal of negative charge will make this anion stable. So the anion in option 2 is going to be more stable. Anion in option 3 can also be stabilized by oxygen over here, but this oxygen is relatively far away from CO minus as compared to the second CO minus. You see, this oxygen is, if you consider this as first position, first, second, third and fourth. So in 2, oxygen is fourth to this COO. Here oxygen is 1, 2, 3, 4, fifth to CO. And nearer the electron withdrawing group, better the dispersal of negative charge, meaning better the withdrawal of negative charge, hence more stabilization of this anion. More the stabilization of anion, stronger the acid, which means 2 is going to be more acidic than 3, and least is going to be 1, because in 1 there is no electron withdrawing group present that can stabilize. Rather, cyclohexyl ring will show electron donating inductive effect that will donate electron, meaning negative charge will increase, and we call it as accumulation of charge. Accumulation of any charge will always bring destabilization. The correct order is 2, 3, 1. 2, 3, 1 is right option. Option B here. Okay guys, I'm hoping that you guys are understanding what we are doing here. Yeah, and all these questions that we are doing are basically a revision of theories or the concepts what we have learned in the previous chapters. So here the question was from carboxylic acid, but of course we use the concept from GOC as well. Number 24, the propanoic acid or propionic acid with Br2 in red phosphorus or phosphorus yields a dibromo product. The structure would be, well, I want you guys to recall this reaction. RCH2COOH. When we treat this with red phosphorus plus Br2 followed by hydrolysis, this results in the formation of substitution of one hydrogen atom at alpha carbon atom with the halogen which we have used here. You can see red phosphorus plus bromine upon reaction with carboxylic acid carrying alpha hydrogen atom undergoes alpha halogenation. This reaction is known as Wallah-Zelinsky reaction. And if you use this reagent in excess, remaining H will also be substituted by the halogen given. This, upon further treatment with red phosphorus plus Br2, will substitute the remaining H as well, and we'll be getting Rc Br2 and COOH. So which option fits well according to the statement that is given? Statement belongs to HVZ reaction, which is alpha halogenation reaction, and excess of reagent will always give you the exhaustive halogenated product at the alpha carbon. So both H's will be replaced by 2-bromine, but at alpha. If you look at option A, carboxylic acid, so this is alpha carbon, this is beta. Bromination does not take place at beta, not our choice. Here, product is not carboxylic acid. They have just given intermediate. The next step which is supposed to take place after this haven't been mentioned, so this cannot be our choice. Option C, yes, option C fits well. Propanoic acid meaning acid containing 3 carbon. So with respect to acid at alpha carbon, we are having 2-bromine. So C is the right choice. Of course, B is not the correct choice because one bromine is alpha, other bromine is at beta. Not the correct answer. Next question, number 25. In a set of reaction, acetic acid yielded a product D, meaning this has given product D. What is the structure of product D? Okay, so we have to find out D here. Okay, guys, let's write down the reaction. Starting with acetic acid. So we are writing reaction here. Treated with SO2Cl2. SO2Cl2 is a chlorinating agent. It chlorinates alcoholic OH or OH of carboxylic acid. We've got CH3 C double bond OCl, which upon treatment with benzene in presence of AlCl3 will undergo Friedel-Crafts acylation. So one of the H of benzene will be substituted by acyl group. So you can simply, for the sake of remembering the reaction, you can remember like this. So we'll be getting acetyl group introduced on benzene, meaning acetophenone will be the product. Which is then treated with HCN. So how will we write the product? Cn minus will attack at carbonyl carbon. This bond will break towards O. O minus will accept proton from here. So our intermediate will then be CH3 carrying cyanide. And up here we have got OH. This compound is then further hydrolyzed. So upon hydrolysis, cyanide group here will be hydrolyzed to COOH. Hence the product would be COH, CH3 and COOH. So yes, you can see we have got chiral compound once again here. Which option is saying so? Yes, option D here. Right, everyone? So that's our product. 2-hydroxy-2-phenyl propanoic acid. Next question, 26. The OH group of an alcohol or the COOH group of carboxylic acid can be replaced by chlorine using. Alright guys, see in the previous question we discussed the same thing. SOCl2 is a chlorinating agent that is used for the replacement of OH. Now other than this, several other reagents that could have been used. If not SOCl, we could have also used PCl3 or PCl5. These all are chlorinating agents which are used to chlorinate OH of either alcohol or carboxylic acid. So the set of reagents available for such chlorination are SOCl2, PCl3 or PCl5. So which option says so? Yes, the first one is PCl5. So yes, we do use this reagent. So either you use, if your substrate is either acid or alcohol, this two upon treatment with PCl5 will chlorinate OH. So the product will be either RCl or RCOCl. And the byproduct is going to be POCl3 plus HCl. So yes, among the option given, it's option A which is fitting well in this question. Next one, number 27 for you all. In a set of given reaction, acetic acid yielded a product C. Alright, again, this question is similar. By the way, guys, the previous one was also acetic acid, but we were getting aromatic compound. Here we don't see. Yes, here there could be aromatic, but different than the previous. So these two are certainly different question. Yes, benzene and acetylene we have. We don't have any acetylene here. Okay. See now, they have given us acetic acid. They have asked us to treat this with PCl5 to give you A. So acetic acid with PCl5. Let's write down the reaction. OH will be replaced by chlorine. So A is acetyl chloride, which is treated with benzene. In presence of anhydrous AlCl3, so this is Friedel-Crafts acylation. Let's say HCl have been removed. We will be getting formation of CH3C double bond O connected to benzene straight away. That is your B. Now they are saying this B is treated with ethyl magnesium bromide in an ethereal condition followed by hydrolysis, let's assume. So ethyl magnesium bromide, C2H5 MgBr. Well guys, we are aware that in Grignard reagent the value of R is always considered as R minus since the bond between Mg and alkyl is predominantly ionic. So the C2H5 will attack at this carbon, this bond will break towards O, making it O minus. And let's see if we are carrying out further hydrolysis as second condition. This is first and second. Upon hydrolysis, acidic condition, this O minus will accept H plus. So the product will be CH3COH, ethyl group is attaching to carbon, and then there is phenyl ring connected here. So the product is a chiral carbon once again carrying OH, methyl, ethyl and phenyl. Chiral carbon carrying OH, methyl, ethyl and phenyl ring. So isn't it option D, everyone? Option D is right choice. Number 28. Which one of the following compound will react with sodium bicarbonate solution to give you sodium salt and carbon dioxide? Well, understand one thing. Here the reagent that they have given is sodium bicarbonate, which is a base. And always simply remember one thing. Any base reacts with only those acid which is stronger than its conjugate acid. Any base will react with only those acids which are stronger than its conjugate acid. Meaning, if NaCO3 is a base, what is its conjugate acid? How do you find out conjugate acid? If I dissociate Na plus and SCO3 minus. So to this anion, if you add H plus, you will get conjugate acid. To this anion, if you add H plus, you will get conjugate acid. So HCO3 minus plus H plus will give you what? H2CO3. So H2CO3 is a conjugate acid of NaCO3, which means now this bicarbonate will react with all those acids which are stronger than H2CO3. So any acid stronger than H2CO3 will react with this bicarbonate. So among the option given to us, first molecule is alcohol. Second molecule is alcohol. First one is acetic acid, which is carboxylic acid. And then we are having phenol. So among these four acids, carbonic acid, carboxylic acid, alcohol and phenol, if you find out their order of acidic strength, then the strongest acid among all this is carboxylic. Among these four I'm talking about. In between there could be some other as well. After carboxylic acid, next is carbonic acid. Then comes phenol. And then comes alcohol. Now apply the concept that we discussed here. Bicarbonate, or for that matter any base, will react with only those acids which are stronger than its own conjugate acid. So bicarbonate's conjugate acid is H2CO3, carbonic acid. Anything which is stronger than this acid, with that this bicarbonate can react. So the only acid among the four which they have given is carboxylic acid, which is stronger than H2CO3. These two being weaker, they will not react with bicarbonate. Hence RCOOH is the only acid will react, meaning it is acetic acid that will react with NaCO3. And if you have to write the complete reaction, well, I'll write it down here. Let's see, you're having carboxylic acid RCOOH treated with sodium bicarbonate, Na plus HCO3 minus. So this bicarbonate will accept H plus from here. So upon loss of H plus, this carboxylate ion will be balanced by Na plus. So we will be getting RCO ONA plus. Now H plus upon H plus when accepted by this CO minus will give you H2CO3, right? If this O minus accepting H plus, it will become H2CO3 carbonic acid. Carbonic acid being unstable, this decomposes to give you H2O plus CO2. Meaning because CO2 is not highly soluble in water, it evolves off to give you H2O and CO2. So when CO2 comes out, it comes out in the form of effervescence. That's what they're asking. So we're getting salt and release of CO2. Salt and release of CO2. Which one of the following compound will react with bicarbonate to give you salt and CO2? So it is carboxylic acid. So base will react with only those acids which are stronger than its own conjugate acid. According to option given, it is carboxylic acid. So guys, next question, number 29 for you all. Benzoic acid gives benzene on heating with X, okay? And phenol gives benzene upon heating with Y. X and Y are respectively. Well, why don't we write it down and see and try to recall the reagent then? Benzoic acid. Let's say this is benzoic acid. They are saying this is treated with X. Give you benzene. And phenol gives again a benzene. Okay. What set of reaction are we using? Well, second reaction is the simplest of all. We know that process for converting phenol into benzene. It's a reduction of benzene where we heat phenol with zinc dust. So zinc dust being reducing agent will just take away oxygen and you'll get benzene. And first one, benzoic acid upon reaction with mixture of NaOH plus CaO, which you call it as soda lime. NaOH plus CaO 1:3 proportion. So first NaOH reacts with this benzoic acid and convert that into sodium benzoate. So this will write it as ONA. And now upon heating with soda lime, will eliminate Na2CO3, sodium carbonate, Na2CO3. So H will satisfy this valency to give you benzene. So the two reagent, X is this and Y is zinc dust. So X is soda lime, NaOH plus CO, and Y is dust. So this is not our choice. Zinc dust, no, not our choice. X and Y respectively. So this is also not our choice because X has to be soda lime, and then B has to be zinc dust. The right choice is option D. Now guys, next question number 30 for you from 2008. The relative reactivity of acyl compounds towards nucleophilic substitution reaction is of the following order. Okay. Everyone, let us assume we are having some acid derivatives. Acid chloride, acid amide, ester or anhydride. Now whatever acid derivative we take, they contain some leaving group here. If it is acid chloride, chlorine will be leaving group. If you have acid anhydride, carboxylate will be leaving group. If it is ester, alkoxy group will be leaving group. When we allow such compound to react with nucleophile, this nucleophile attacks at the deficient carbon, bond breaks to make it O-. So we get formation of R, C single bond O-, leaving group, and here we get nucleophile. You can see sp2 carbon converted to sp3, and then this negative charge delocalizes and leaving group leaves. So the product form here is R, C double bond O, Nu. So if you see difference here, this leaving group have been substituted by nucleophile. So one nucleophile substituted by another nucleophile, so it is nucleophilic substitution, and the nucleophilic substitution has taken place at the acyl group, so we call it as acyl nucleophilic substitution reaction. The rate of this acyl nucleophilic substitution depends upon how faster the leaving group is leaving. So faster the leaving group leaves, faster the rate of reaction. Hence we say better leaving group will give this acyl nucleophilic substitution reaction at a faster rate. So what we have to decide now? Among the option given, we'll have to find out which is a better leaving group. So we must not forget poor bases are good leaving group. Poor bases are good leaving group. So for the species to be good leaving group, it should be poor base. Poor bases are good leaving group. So if you check all the options, well, in acyl chloride, let me write down all the structures. In acyl chloride, the leaving group is Cl. We are talking about leaving group here. Next, acid anhydride. The leaving group is carboxylate. Next is ester. RCOOR dash. The leaving group is alkoxy group. And in amide, RC double bond to NH2. The leaving group is amide. NH2 minus. Now, out of this leaving group that we have got, whichever is a better leaving group, it will have a faster rate of reaction. And we know that poor bases are good leaving group. So poor bases are always obtained from the strong acid. So we'll have to find out the corresponding acid first. So Cl minus is a conjugate base of HCl. RCO minus is a conjugate base of RCOOH. RO minus is a conjugate base of alcohol. See, I'm just adding H plus here to this anion. NH2 minus is a conjugate base of ammonia. And now guys, tell me, what is the order of acidic strength of this? Isn't it that HCl is the strongest acid? If it is strongest acid, then its conjugate base is going to be poor base. Strongest acid conjugate base is poor, and poor bases are good leaving group. So this is the best leaving group. After HCl, second best acid among these three is carboxylic acid. If carboxylic acid is strong acid, its conjugate base is going to be poor. I mean, in comparison of other two. So second best leaving group is carboxylate. Between alcohol and ammonia, alcohol is a better acid, so its conjugate base is relatively poor than NH2 minus. Poor bases are good leaving group. So this is third best, and this is the fourth best leaving group. So wherever in this acyl leaving group, the leaving group is Cl minus, is going to be the best leaving group. So order of reactivity will be fastest with the best leaving group. Hence you will say acid chloride react fastest, then anhydride, then ester, then amide. So where is that order? Here it is. Acid chloride, then anhydride, then ester, and then the amide, acid amide. So the right choice is answer option C. So relative reactivity rate of acyl compound depends upon the leaving group ability. Better the leaving group, faster the rate of reaction. And that's how we get the corresponding order. So dear student, that was all about another important chapter, and we discussed all the important previous year question from the chapter Aldehydes, Ketones and Carboxylic Acid. So we'll have to stop here today, but I'll be seeing you guys soon in the next chapter, that is amines or nitrogen containing organic compounds. So guys, I wish you all the best. Do practice as many questions you can. Study hard, and I'll see you soon in the next class. Thank you so much for attending this class. Take care everyone. I'll see you soon.